In this video, we're going to learn how to represent chemical equations. So what is a chemical equation? It describes a chemical change, and there are parts of the equation. So the things ahead of the arrow are considered the reactants. Then there's the reaction symbol and the arrow, so it's an arrow, and it points to where the products are being made. So the products are over here. So generally you have your reactants on the left, an arrow pointing to the products, and your products on the right. If the arrow pointing the other way, then the reactants would be on the right and the products on the left, but generally we write these equations in this direction. Again, reactants and products. The reactants or reactant are the chemical or chemicals you start with before the reaction has taken place. We write them on the left side. The products are the new chemicals that are formed by the reaction, and they're found on the right side of the equation. A word equation tells us what happens during a chemical reaction. It tells us what is reacting and what is being produced. So in this example, we have iron and oxygen reacting together to form iron 3 oxide. A skeletal equation shows every chemical name being replaced with its chemical formula. So in this example, iron plus oxygen makes iron 3 oxide. The key thing there, the 3 tells you the charge that's on iron. So we're going to have to figure out what the chemical formula of iron 3 oxide is. But iron symbol is Fe. So we'll write that. So Fe, and remember oxygen's a diatomic molecule. So plus O2 makes iron 3 oxide. So I'm just going to write up here. We have iron, which has a 3 plus charge. And then oxygen has a 2 minus. We'll do the crossover rule. So it's actually going to be Fe2O3. So that's our skeletal equation. We can see that it's not balanced yet. We'll do that in the next step. Remember, subscripts show how many atoms of an element there are in a molecule. So with H2O, you have 2 atoms of hydrogen for the 2 and 1 atom of oxygen. There's no number there, so we know that's 1. The coefficient tells you how many of the molecules there are. So in this example, 3H2O means that we have 3 individual water molecules. Let's practice. So we're going to write the skeleton equations for the following reactions on the next few slides, and then we will balance them afterwards. So for this first example, we have magnesium. So that's a metal, so we just write Mg plus oxygen. Remember, diatomic molecule, so O2, doesn't like to be alone, makes magnesium oxide. So we have to do the crossover rule. So magnesium, it's in the second column of the periodic table, so it has a charge of plus 2. Oxygen has a charge of minus 2. We cross them over. Because it's an ionic compound, we reduce that down, so it's just MgO. The 2's cancel each other out. For this next example, hydrogen and oxygen are both diatomic molecules, so it's just going to be H2 plus O2 makes water, and that's one of the universal molecules everybody knows is H2O. So for the next one, I've already done it. So it's carbon tetrahydride. The other name for this is methane. In some higher years of science, you'll learn about organic compounds and their special way of naming. But carbon tetrahydride is CH4 plus oxygen. Remember, it's diatomic. Makes carbon dioxide and water. So CO2 plus H2O. So again, with molecular compounds, they're telling us how many of each atom, so we don't need to worry about the crossover rule. And then we have to remember that oxygen is a diatomic molecule, so it's always going to be O2. So this next one is a little bit more tricky because we're working with polyatomic ions and 2 sets of compounds, but we can still do it. So lead to nitrate. So lead is Pb, and it's telling us that it has a charge of plus 2. Nitrate is a polyatomic ion, NO3, with a -1 charge. So we know already that we're going to be crossing a 2 down. So we're going to put brackets around the NO3. So the 2 is going to come down and go there. The 1 will cross over. So the formula is PB brackets NO3 brackets 2. So we're going to write that up here. PB brackets NO3 brackets 2. And then potassium iodide. Potassium has a charge of 1. And iodide has a charge of -1. -1, so it's just Ki. And that makes lead to iodide. So we know lead has a charge of 2. Iodine, we know, has a charge of -1 because it's in the halogen column. We cross over. So this is going to be PbI2. And then potassium nitrate. Potassium has a charge of 1. Nitrate, also a charge of -1. So this is just going to be KNO3. So there's our skeleton equation. The last example is copper and silver nitrate. So copper, it's a metal, so it hangs out by itself, Cu. Silver nitrate. Silver has a charge of +1, and nitrate has a charge of -1. We've already seen that one in this video. So it's just going to be AgNO3. And that makes silver, again, a metal, so it's going to hang out by itself. And then copper 2 nitrate. So Cu, copper has a charge of 2. We know nitrate has a charge of -1. So we're going to have to put brackets and bring that 2 down. So it's going to be Cu brackets NO3 brackets 2. So this is how you write skeleton equations. We're not finished yet. You would need to balance all of these equations because the law of conservation of mass tells us that we can't create or destroy matter. It can only be reformed, so we need to have the same number of atoms on the left as we have on the right of the equation arrow. We'll learn that in another video.